Jean-Paul Lomont, professeur roboticien, Académie des sciences, Académie des technologies, directeur CNRS, commissaire de l'exposition permanente robot à Universcience. Maintenant, Cecilia Lasky, elle est aussi prof de biorobotique à l'université et à l'école supérieure Santana de PISA. Elle nous parlera de la nature, à la robotique et Retour. Merci Cecilia.
Merci. First of all, I apologize that I can't speak French. So sorry for this, but I'm sure the students will understand English. Well, hope so. Sorry for that. So we heard that Leonardo studied nature a lot, studied biology, especially for painting, or he started with this because he was not happy with the descriptions of the human anatomy to do his paintings. But then he also studied biology, nature for engineering, for building his machines, especially the flying machines we have seen already. Actually, some, or maybe many of Leonardo's machines were never built. They didn't work. Probably there was a technological gap. So with the materials that he used, like wood and ropes, probably it was difficult to build some of the machines, for example, the flying machines. And this group in Ontario demonstrated that with the technology that we have today, Leonardo's machine could work. This is Leonardo's ornithopter, and he could fly with these flapping wings for almost 20 seconds. But actually, when you build a machine based on the observation of living beings, you learn a lot on these living beings. So Leonardo at the same time explained a lot about the biology, about nature, by building his machines. And this is actually what still happens in engineering. So we look at biology to have new technologies, to develop new technologies, but at the same time, when we build a new technology based on the observation of nature, we learn a lot on the living systems. This is what we call bioinspirational biomimetics in engineering. You probably know several examples, so you probably know this one. I'm sure you all use this this kind of technology. Here, an engineer observed that a plant burr could attach to the fur of his dog quite firmly, and then it could be removed. So he observed this plant burr, he found small hooks, and he invented velcro. So I'm sure you all know this, and he patented this invention and became rich. And in robotics, we try doing the same. There are many examples. This is one of them. And it's quite interesting because it's a robot that can climb over walls, because its feet are inspired to they really get the principle of adhesion of the gecko feet. This is a key issue, understanding the principles in the living beings. This is another example that I'm sure you know, but probably you don't know that it is bio-inspired. Here, this engineer is observing a human bone. And he finds that there are many, how can I say, empty spaces in the human bone. And this reduces the weight a lot, of course. And the parts that you see inside are not randomly oriented, but they are oriented along the lines of force acting on the bone. Do you know who this engineer is? This is Rafael. and actually he solved his problem of building the tallest tower in the world at that time without having it collapsing under its own weight, because the material used was iron, so it was very, very heavy. And he did the same as in the human bones. He oriented this trabecula along the lines of force, and he built the Tour Eiffel. So there are still so many lessons that we have to take from nature for robotics. We want to learn how animals can do things like this, so how complex systems like animals or even plants and like our robots can work efficiently and effectively in a complex world. These are the lessons we want to take from nature. In my institute in Italy, we studied a very special animal, very special for me, because it is a completely soft animal. It's the common octopus. So its body can deform a lot, but they can also grasp objects, manipulate objects, and they can walk underwater. Walking underwater doesn't make sense. It's not efficient with our legs. But the octopus can do that very efficiently because it can shorten and elongate its arms. So we tried to understand the principle, and we demonstrated the principle with this simple soft robot. It's made in silicon. There is a flexible cable inside. So shortening and elongating is very simple. It's just one motor that can pull this flexible cable inside. And with this simple prototype, we could test the principle. So we built this small robot, vaguely in the shape of an octopus, that can walk underwater, can walk on the sea bottom, and explore tiny spaces, for example, and without damaging the sea floor. But the principle is not enough for engineering. You need to build a mathematical model that explains the principle. And we built a mathematical model for underwater legged locomotion. And we built another prototype. This time you don't need that it is in the same shape of the octopus, because what is important is that you use the mathematical model inside it. So we built this other prototype for National Geographic for this mission on a shipwreck. It's not very deep, 12 meters or so. And we showed how this robot could walk on the sea bottom. You see, it's quite efficient in terms of energy and very simple to control. And another important thing is that it can stay in the same location, completely steady, completely still, without consuming energy. You see in this picture, this is the picture taken from the robot. Everything is moving around it, but the robot is completely still. This is quite useful underwater, especially if you don't need to use energy. This is an evolution. This is silver too. The previous one was just silver. And it also takes some inspiration from crabs. So it has articulated legs, as you see. It can go down to 200 meters of depth. And there is a part that stays on the surface. You see it here. So it can communicate with a computer with this surface part of it. And it has some small probes, you see, under the robot. So the robot can push them down in the sand and take samples to check if there are microplastics. You know that this is a quite important problem today, and searching for plastics in the sediment, in the sand, is also very, very important. So with bio-inspiration, what I see as the progress of robotics is a new generation of robots that are more similar to living organisms and that can grow, learn, evolve like living beings, and also self-heal, find their own energy in the environment, and biodegrade at the end of their life. So to help us in many different ways, but also preserving nature itself, as we have seen. This is the place where we do our research in Italy, in Livorno, and I need to thank the funding agencies, but especially the people working with me, and I thank you for your attention.